So far what we've considered in the transfer theorem is the product and second moment of area when the centroid is displaced with respect to the origin of a given system. Now we want to look at another transformation where given an area and its second moment of inertia and product of inertia about a set of axes x, y, we wish to calculate it about another set x prime y prime, which is rotated with respect to the first set by an angle theta. Let us see what happens in this case. So, if I were to calculate I x prime y x prime in the rotated set, this is going to be equal to integral y prime square dA. I y prime is going to be equal to x prime square dA, and I x prime y prime in the second frame is going to be x prime y prime dA, where we choose a small area dA whose coordinates in the original system are x and y, and in the new system are x prime y prime. We can find out the relationship of Ixx prime with those similar quantities in the unrotated frame by simple transformation laws of x and y coordinates. So let us do that now. So what we are given is an area, and we wish to calculate its second moment of area and product of area with respect to a set of axes x prime y prime when they are given in x and y. We know from our previous lectures that x prime for a given point is equal to x cosine of theta plus y sine of theta. Similarly, y prime is equal to minus x sine of theta plus y cosine of theta. Using these, let us find what I x prime is. From the previous slide, we know this is equal to y prime square dA, where dA is a small area chosen. Y prime square is going to be equal to integral minus x sine theta plus y cosine of theta square dA, which I can write as x square dA integral sine square theta plus integral y square dA cosine square theta minus 2x y dA sine theta cosine of theta. But x square dA is nothing but Iyy. Y square dA is nothing but Ixx, and xy dA is nothing but Ixy. Therefore, I can write this quantity as, let us go to the next page, I x prime as I yy sine square theta plus I x cosine square theta minus I xy 2 sine theta cosine theta, which can be written as I yy divided by 2 1 minus cosine of 2 theta plus I x divided by 2 1 plus cosine of 2 theta minus I xy sine of 2 theta, which is nothing but I xx plus I yy divided by 2 plus I xx minus I yy divided by 2 cosine of 2 theta minus I x y sine of 2 theta. Thus, if I know the second moment of area and product of area in one frame, I can calculate it in the rotated frame. Let us do the same exercise for I y prime, which is going to be equal to x prime square dA, but I know x prime is equal to x cosine theta plus y sine of theta, and therefore I can write this as integral x square dA cosine square theta plus integral y square dA sine square theta plus 2 integral x y dA sine theta cosine of theta, which is, this is nothing but I y, this is nothing but I x, and this is nothing but I xy. So this whole thing can be written as I y over 2 1 plus cosine 2 theta plus I x over 2 1 minus cosine 2 theta plus I xy sine of 2 theta, which is nothing but I x plus I y divided by 2 minus I x minus I y divided by 2 cosine 2 theta plus I xy sine of 2 theta. Last, we calculate I x prime y prime, which is nothing but x prime y prime dA, which is equal to integral x cosine theta plus y sine of theta times minus x sine theta plus y cosine theta dA, which comes out to be integral minus x square sine theta cosine theta plus xy cosine square theta minus xy sine square theta dA plus y square sine theta cosine theta dA. This is also dA. X square dA is nothing but minus I y. This can be written as sine 2 theta divided by 2 plus y square dA is I x sine 2 theta divided by 2, and xy dA is nothing but I xy cosine square theta minus sine square theta is cosine 2 theta. So I x prime y prime is nothing but I x minus I y divided by 2 sine 2 theta plus I xy cosine of 2 theta. Let us summarize. What we are looking for is, if we know for a body the products and second moments of inertia in one particular frame, how about its values in the rotated frame? In the rotated frame, let me now write it in blue. I x prime is nothing but I x plus I y divided by 2 plus I x minus I y divided by 2 cosine 2 theta minus I xy sine of 2 theta. Similarly, I y prime is going to be I x plus I y divided by 2 minus I x minus I y divided by 2 cosine 2 theta plus I xy sine of 2 theta, and I x prime y prime is going to be equal to ixx minus iyy divided by 2 sine of 2 theta plus ixy cosine of 2 theta. What these transformation laws give me is, if I am given the second moment and product of area about a set of axes, I can calculate about any other set of axes which is rotated with respect to the first set of axes. Let me just illustrate this thing by a couple of examples which are very interesting. Suppose I take a circular area. For a circular area, no matter how I choose my rotated set of axes, let's take a third one like this, the circle always looks the same, and therefore ixx and iyy should always come out to be the same no matter what the cosine theta or sine theta is, and ixy should always come out to be 0. Let us see if that happens. So ixx we saw already is x prime is ixx plus iyy divided by 2 plus ixx minus ixy divided by 2 cosine of 2 theta minus ixy sine of 2 theta. Now for a circular area, ixx is equal to iyy and ixy is 0, and therefore x prime is going to be equal to ixx, and y prime is also going to be equal to ixx equals iyy, and x prime y prime, which is equal to ixx minus iyy divided by 2 sine of 2 theta plus ixy cosine of 2 theta is also going to be 0. This is expected for a circle. What is very interesting, that the same thing comes out to be true for a square. Let us look at that case. So if I take a square of side A, we have already calculated that ixx for such a square is a raised to 4 over 12, and so is iyy, where these are the x and y axes, and ixy is 0. The fact that ixx and iyy are equal and ixy are 0 makes these quantities the same no matter which other frame you look at. So let me write in red x prime which is equal to ixx plus iyy divided by 2 plus ixx minus iyy divided by 2 cosine 2 theta minus ixy sine of 2 theta is going to be equal to ixx again. Similarly, y prime is going to be equal to iyy, and x prime y prime is equal to ixx minus iyy divided by 2 sine 2 theta plus ixy cosine 2 theta. This is always going to come out to be 0 no matter how much you rotate the axis by. So for a square about any set of axes, x prime is always equal to a raised to 4 divided by 12. y prime is always equal to a raised to 4 divided by 12, and x prime y prime is always 0. Having given these two examples, I use these transformations to define something called the principal set of axes. So given an area, I look for those set of axes, let me call them x and y, so that ixy is 0, or rather give them a special name ix bar y bar, so that ix bar y bar is 0. How do we accomplish that? since we already know that I x bar y bar is going to be equal to I xx minus I yy divided by 2 sine of 2 theta plus I xy cosine of 2 theta, this implies that if I choose rotate the new set of axes such that tangent 2 theta is equal to 2 I xy divided by I yy minus I xx, I will get new I x bar y bar is equal to 0. Such a set of axes where the product of area vanishes is known as the principal set of axes, and you can see from the construction that you can always find one set of axes because tangent 2 theta is varies from minus infinity to plus infinity. You can always find a set of axes where the product of area would be 0. An interesting fact about the principal set of axes is that about the principal set of axes, the one product of area vanishes, and 2 the moment or the second moment of area is maximum about one axis, say the x axis, and minimum about the other one. If it is maximum about the x axis, the other one is going to be y axis. Let us see how does that come about. So let us look at I x bar which is I xx plus I yy divided by 2 plus I xx minus I yy divided by 2 cosine 2 theta minus I xy sine 2 theta, and ask for a new frame such that I x bar is a maximum. So for that I got to do I x bar over d theta is equal to 0, and when I do that here, this implies that I xx minus I yy divided by 2 times minus 2 sine 2 theta minus 2 I xy cosine of 2 theta is equal to 0, and that immediately gives me that tangent of 2 theta is equal to I xy times 2 divided by I yy minus I xx. So when I accomplish by this rotation the fact that the product of area vanishes, at the same time it maximizes or minimizes the moment of area. This equation has two solutions. Suppose one of the solutions is theta equals alpha, and theta equals alpha plus pi by 2 is also a solution. So by rotating it by angle alpha, I maximize or minimize the moment of inertia about that particular axis. You can show that about the axis at alpha plus pi by 2, it will be the other way. If it maximizes at alpha plus pi by 2, it will minimize, and vice versa. So we found a set of axes principal such that not only the product of area vanishes, the second moment of area is also either maximum or minimum. If it is maximum about the x axis, about the other y axis, it becomes a minimum. If it is minimum about the x axis, it becomes maximum about the other axis, the y axis. Having made this point, let me now define something for you which is known as the polar moment of area. This is usually written as J, which is nothing but I xx plus I yy, and therefore is equal to integral x square plus y square dA or r square dA. Given any area r square for a small area chosen is independent of which set of axes we are talking about. So this is independent of the set of axes chosen. And through this discussion you also see that for a square any set of axes is the principal set of axes, because as we have seen earlier, the principal set of axes gives product of area 0 and second moment of area maximum or minimum. For a square, any set of axes gives you product of area 0. So therefore any set of axes chosen for a square or a circle is the principal axis. What we have covered in this lecture so far is the second moment and product of an area. A related quantity which we will talk about in later lectures when we discuss dynamics of rigid bodies would be the moment of inertia and product of inertia, and we will be using it then in describing the rotational motion of a rigid body.